I'm going to show you the golden rectangle. I'm going to start here with a square that's 2 on each side, so a square of side 2. I want to go to the midpoint of this side and kind of bisect it here, so that length is 1 and that length is 1. Then I'm going to draw this diagonal in. Let me get a ruler here. Draw this diagonal in that goes from this midpoint up to that vertex of that square. And then what I want to do is drop that down, that length down, and extend this side right here to meet that. Now when I do that, then the rectangle that I get is called the golden rectangle. Let me see if I can just quickly draw it in right here. There's my golden rectangle. And so what I want to do is find the ratio of the length to width in the golden rectangle, because in mathematics that's a very special number. So if I look in this little right triangle right here, I see that this side is 1, this side is 2, because that was my original square, and so by the Pythagorean theorem I know that this side is going to be square root of 1 squared plus 2 squared, square root of 1 plus 4, or square root of 5. So this length is square root 5. That means that this length right here is square root 5. And this little length is 1, so if I want the ratio of length to width in the golden rectangle, the length is 1 plus square root 5. And the width is this width right here, which is just 2. So this number right here, 1 plus square root 5 over 2, it's an irrational number, but it's also called the golden ratio. Very special number in mathematics. If you work this out on a calculator, it's approximately equal to 1.618. Of course, I can't write it as a decimal because it's an irrational number. So the golden rectangle, when I find the ratio of the length to width in that, I end up with what's called the golden ratio. Now I want to show you a little postage stamp from Japan that kind of this little derivations on it, as you can see, sort of vertical rather than horizontal the way we did it, but very important derivation in mathematics, so important that they actually put it on a postage stamp. Now I want to walk over to the other board here and look at another golden rectangle. Alright, this time I want to make a golden rectangle from a square of side 4 rather than a square of side 2. So I do the same thing. I go to this midpoint right here. That means that each of these two lengths is 2. And then I draw in this diagonal right here, and then I want to drop it down like this, form this rectangle, and that will be another golden rectangle because I've derived it in exactly the same way I did with my first one. Well, that means that it's similar to my other golden rectangle, so the ratio of length to width should come out to be that golden ratio. So let's take a look and see. Let's see, this side right here is 2, this side is going to be 4, so this side will be the square root of 2 squared plus 4 squared, so I have 2 squared is 4, 4 squared is 16, 4 plus 16, square root of 20. Now when I want the ratio of length to width, okay, that will be 2 plus this length right here is going to be the same as this length, so square root 20. All divided by the width, which is 4. So just to go over that again, here's the width, 4. Here's the length right here, which is 2, plus this length, which is the same as this length, or square root 20. So 2 plus square root 20 for that. Well, this should come out to be the same as my other one, so let's see what I can do here. 2 plus square root 20 in simplified form, that's going to be square root of 4 times 5. I can take that 4 out as 2. Leave this 5 inside the radical, and that's all divided by 4. Okay, so 2 plus 2 square root 5, 2 square root 5 being the same as square root 20. I'll factor a 2 from the numerator, 1 plus square root 5. The denominator I'll write as 2 times 2, and let's see, did that go off the screen? Yep, it sure did. Hang on just a second. Okay, there I've moved it so we can see it now. 2 times 1 plus square root 5 over 2 times 2. Those 2's divide out, and I end up with 1 plus square root 5 all over 2. Same number I got before for the golden ratio. So any golden rectangle, regardless of what size square you start with, will always end up giving you the same ratio for length to width, and that ratio is called the golden ratio. Now I want to go back to the first golden rectangle that we worked with and look at it for a second. So one of the interesting things about the golden rectangle is that when I construct it like this little rectangle that I get over here also turns out to be a golden rectangle. So the big one's a golden rectangle, but so is this one right here, and we can show that by finding the ratio of length to width. So in the little blue rectangle, okay, I have the ratio of the length to width. Well, that's the length in this rectangle. This is the width. Well, what's the width? Well, this length right here is square root 5, that whole thing. That length is 1, so this length right here on the inside, this must be square root 5. That's the whole length minus 1. So if I find the ratio of length to width in my little blue rectangle right here, I'm going to end up with the length of 2 divided by the width of square root 5 minus 1. Well, this should come out to be the same thing. It should be 1 plus square root 5 over 2. How can we show that? We can show that by rationalizing the denominator on this expression. So to do that, I'm going to multiply by square root 5 plus 1 in the denominator and square root 5 plus 1 in the numerator. In the numerator, I get 2 times square root 5 plus 1. And in the denominator, I get square root 5 squared minus 1 squared. So 5 minus 1, which is 4. Let's see if I'm going to have enough room right here. And that comes out to be 2 times square root 5 plus 1, all divided by 4, which is 2 times 2. And that means that these 2's divide out, and I end up with 1 plus square root 5 over 2 for the ratio of length to width in this little rectangle right here. Now I want to show you a postage stamp, another postage stamp that has the golden rectangle on it, and you can see this little rectangle and a bunch of other ones also. So let's take a look at it. Now when you look at it, you notice that there's a little spiral that comes off of this, and in fact there's a bunch of little golden rectangles that spiral on down smaller and smaller. So in fact, if this is a golden rectangle right here, the little blue rectangle, that means it must have come from some square itself. Well, that means that this up here is also a golden rectangle, and so it must have come from some square itself. That's a golden rectangle, it came from some square, so on and so forth. So you can see that those golden rectangles spiral down further and further as small as you want to get. So every golden rectangle also contains an infinite number of other golden rectangles, all with the same ratio of length to width.